covalent bonding is essentially classically defined as the sharing of electrons. Now, and we'll find out that in actuality, in reality, is the overlap of what we call bonding orbitals, to hybridized orbitals or orbitals ready to undergo bonding. But the idea is a covalent bond involves an electron pair. So one covalent bond or molecular bond is equal to simply an electron pair. And that is a diamagnetic condition. In other words, the pairing of opposite spins of the electrons. Okay, let's see. Molecular compounds. What's an example of molecular compound? Methane, CH4, where hydrogen is considered a nonmetal. So it is important that we are able to draw dimensional, two-dimensional, and three-dimensional diagrams of the substance or the compound so that we can make decisions on how its chemistry changes. If we look at methane, for example, we would see this kind of structural formula, if you will, and some applications or some descriptions of what it does. And you'll see a three-dimensional also. This is the three-dimensional structure of methane, and it's called a tetrahedron. It's a tetrahedrally arranged structure. Well, in drawing these, again, it's very important that you be able to do so for a given formula so that you can make decisions about the chemistry. Well, drawing these follows certain rules in terms of, well, what do you do first, second, third to draw out something like this? Well, this one is based upon what we call the Lewis dot structure. And the one over here that's in tetrahedral form is what we refer to as geometric. And there are rules, like I say, on drawing each of these and representing the molecules so we can define the chemistry. Well, this represents part of what we call the molecular dynamics section you'll see in your outline if you look down under topics. But this is where we are right now. So the first thing I'm going to do is teach you how to draw out two-dimensional structures given formulas and then make decisions about the chemistry. So that's my objective for today, is to try to get through this and what we call molecular dynamics. Anyway, this is referred to as, and I invented this a bunch of years ago, AVOBEC method of drawing Lewis dot structures. Now, as I go through it first time with you, it will seem kind of detailed. But I assure you, after we've done about 3 or 4 molecules and formulas, you'll be doing this stuff in your head. And you'll be jumping over certain sections of the process very, very quickly. But the AVOBEC is an acronym that means arrange your elements in other words, the two-dimensional arrangement that you think the elements from the formula will give you. Well, we're familiar with methane like this, but not all of them are as easy to identify. You may be able to draw several contributing structures for the same set of elements. Well, that's what I'm talking about here, so that you have a general idea of how that two-dimensional molecule is going to look. Then you have three calculations here. Calculate Ca valence number, calculate octet number, and then you calculate your bond number. The valence number is the number of valence electrons associated with a given compound, a formula that they give. The octet number represents all of the electrons involved in the bonding. Everything's paired. I'll show you. You'll understand in a minute. Bond number out of this is the number of covalent bonds that will be in the molecule. And we'll do methane first. You'll see it has 4 as you expect. Okay, once you get through your number of bonds, then you enter your electrons. Now, what that means is you enter your bonds, either in bonded pairs. You got two options here. Bonded pairs, which represents one of the covalent bonds, and non-bonded pairs. Oxygen, nitrogen, and the halogens have non-bonded pairs. For example, if I had water, these would be, I'd put these little pairs next to oxygen like that, and that would represent two non-bonded pairs. Of electrons. See? But anyway, then you check your octet. Now what that means, except for hydrogen, is a duet. The structure you drew, or the arrangement that you made back at step 1, is correct if your octet checks around each element, except for hydrogen, which is duet. And so I want to go through this and show you how it's really an easy procedure. So we'll go through this for methane. So first thing, you're given a formula, and then you arrange it in a format that you think it will represent. Now I'll show you some that have multiple structures here in a minute. Then you calculate your valence. Move it up here. Your valence number. I usually write just V number or something like that. Well, that's the number of valence electrons for each element involved in the compound. So what do you have in this compound? You have 4 hydrogens and 1 carbon. So I'll write 1 carbon plus 4 hydrogens. And when you look on the periodic chart, you see that carbon is in group 4. So that means it has 4 valence electrons. We'll see some with nitrogen, which will have 3, oxygen 6, halogens will have 7 valence electrons. Hydrogen, being in the first group, has 1 valence electron. So we simply 1 times 4 plus 4 times 1 gives us 8, and that's our valence number. That's it. Don't make it complicated. The octet number is when everything is full. This is real simple. Just listen. Everything, regardless of the element, is an 8 when it's filled, except for hydrogen, which is 2. So it's a no-brainer when I write out the octet number. Still 1 carbon plus 4 hydrogens. But when carbon has completely bonded all of its bond sites, it will have bonded and it will show 8 electrons. So I have 1 times 8. And if I had chlorine in it'd be chlorine times however many are there. 8 for chlorine. For any element except hydrogen is 8. Whatever you use. And in the covalent bonding. Now, there is an exception if you started working with ionic compounds, but this does not apply in what we're working with to ionic compounds. This is everything here is going to be molecular compounds. So you either have an octet or duet for hydrogen. So here's 4 times 2. So that's 16. So that's your octet number. The object of getting these two is so that you can determine from this how many covalent bonds are in the molecule. So that's your bond number. Just your number of covalent bonds. It's the octet number minus the valence number divided by 2. And you'll see me write O minus V over 2 like that, just incessantly as I would go through this. So that's 16 minus 8 over 2, 8 over 2, or 4 covalent bonds in this molecule. Okay. Now, our next step is to enter electrons, enter bonds, and electron pairs. Okay, really is what I'm telling you to do. If it has a non-bonded pair, then we'll fill it up. I'll show you that in a minute. Okay, here is a bond, 1, 2, 3, and 4. Carbon does not carry non-bonded pairs in the neutral form. Now that'll make sense as we go through, hopefully. But then, once you get through that, then you check the octets, or duets, by drawing a circle around the electron pairs and the element. Take carbon, for example, here. And so I draw a circle around that. And I have 4 bars. You recall from last class, a covalent bond is one of those bars up there. That's 2 electrons. So that's 1, 2, 3, 4 electron pairs. If I drew it out in the dot structure, of course you'd see this. You're probably more familiar with that. In that format. So if I drew a circle around that, I would count 8 electrons. Okay, so that satisfies the octet nature of carbon. Then you check bonding for hydrogen. You recall that covalent bonding is orbital overlap. Well, I'm showing you 4 overlapping orbitals here in a graphic way. And in hydrogen circle, you have a maximum of 2 electrons. Hydrogen valence is 1, it only gains 1. So if that checks out for all of the elements in the compound that you've drawn, then fine. This is an acceptable structure. And it might be, or it might not be, the compound under study. So, example. Okay, that was the first time through. We've got several to deal with. Okay, let's do C2H6O. Okay, so that's all you're getting. Well, I'm telling you right now, that has 2 acceptable formulas, which lead to 2 different molecules. Now, what that means is the AVO-Beck is good for drawing the molecules, and that's it. To identify the molecule is a different story altogether. To identify, you have to go to some, say, instrumental method where you stick it in an infrared spectrophotometer and find out what it is. All right, hey, I'll show you. I can draw 2 structures for this that will ultimately turn out to be correct structures. Now, the sophistication of instrumental analysis today is such that it will spit this stuff out almost instantaneously when you're working with molecules. Mass spectrometers are really in the state, but this is, say, a basic idea of how to deal with these Lewis structures. Now, I can also draw this, and it will show to be a correct structure also. So what I'm saying is that this AVO-Beck is a true procedure for drawing the molecules in Lewis dot structures. Sometimes they have multiple molecules that are pop out of the procedure. Okay, let's run through the AVO-Beck. All right, we've gone these arrangements. So we need a valence number. Okay, I have 2 carbons and 6 hydrogens and 1 oxygen. Now you'll do the same thing for your octet number: 2 carbons, 6 hydrogens, plus 1 oxygen. Except here, carbon would be 8, hydrogen would be 2, oxygen would be 8. So it's either 8 or 2 in the octet. So we can calculate these two numbers. So that it'd be carbon is 2 times 4 for valence, 6 times 1 for hydrogen, and 1 times 6 for oxygen. So we have 8, let's see, that's 12, 20. So your valence number in that case is 20. Everybody still good? And this is, all you do is look on the map, periodic table, and you come up with the valence number, okay? Octet number is, you change all this 2 or 8. So that's it. 2 times 8 plus 6 times 2 plus 1 times 8 is equal to whatever that sum is. Of course, that's 16, 12, 8, and 10, 28, 36. 10, 20, 28, 31, 2, 3, 6, 36. Everybody good? Any questions? Okay, now, purpose is to get the bond number. Octet minus valence over 2. So you've got your octet number, 36. Your bond number, your valence number is 20 divided by 2. That's 16 over 2, or 8 covalent bonds you have to put into that. Now, these are bonded pairs between elements. Okay? Now, the point here is we're going to have some electrons that are not between elements, and those are the non-bonded pairs we mentioned a moment ago. So, kind of check mark that. So I have to place 8 bars or 8 electron pairs in each of these drawn structures. So here's 1, 2, 3, 4, 5, 6, 7, and 8. So, of course, I've worked these out in great detail over the years, and I know what's coming. So, but these are good illustrations of what to deal with. Some of them are not quite as easy as this. 1, 2, 3, 4, 5, 6, 7, 8. So both of those are legitimate in terms of absorbing all the covalent bonds that we've calculated here. Now we need to check the octets for the structure. And everything checks except this one. On this one. You have 2 bonded pairs, which represents only 4 electrons. How many must you have? 8. It's either 8 or 2. Okay? Complete that octet with what we call non-bonded pairs. Oxygens or group 6 elements, if they are in a compound, will carry 2 non-bonded pairs. Nitrogens will carry 1. Halogens will carry 3 non-bonded pairs. We'll show you that in a second. Then we got several more to do here. It's probably absorb the rest of the day, probably. Let's see. Yeah, pretty easily. So after you go through and circle everything, and you've got 8 electrons around every element, your conclusion is, well, that's a possibility. Now I would have to take it to instrumental analysis to determine what compound I really have that I'm working with. This is ethanol. This is dimethyl ether. You sniff them and tell the difference on those, but you really don't want to use a sniff test on a lot of stuff. And so, anyway, so you should start seeing the pieces fall in together. So as we do more, you really will see them and start doing things in your head. You really will. Okay? Any questions so far? CH3NH2. That's called a methylamine, if you want to know. It's an ammonia derivative. It's ammonia with a methyl group on it. But at any rate, what is the Lewis structure? Now, for your purposes and test day, to save time, I will draw the arrangements for you. But if you were working on a molecule trying to figure out what it is, then you might have to draw out 5 or 6 options. Well, we don't have time to do that. Okay, so you're really going to start at the valence, octet, bond, and then put your electrons in and the structure. Because I'm going to come up here and give you on test day this and say, determine the number of bonds and how many non-bonded pairs does this structure have, and ask questions like that. Okay? Okay. So first thing is our valence number, then our octet number, then we want the number of covalent bonds, then we just put them in the molecule, check, see if everybody's got 8, and if it doesn't, like nitrogen won't, we'll have to put in a non-bonded pair to fill up the 8. So a valence number, here is, we've got 1 carbon, 1 nitrogen. Now, sometimes people will write formulas like that to emphasize a substituent group. That's an amine substituent group. So they will separate that away from the rest of the molecule. Now, you could combine all that. CH5N, same thing. Okay, but anyway, plus 5 hydrogens. And you'll do this twice, but one will be valence, and one will be your octet, and then the octet minus valence over 2 give you your number of covalent bonds. See how that works? Okay, so carbon's 4, nitrogen's 5 on the valence in group 5, and hydrogen is 1. So we have 10, 11, 12, 13, 14. Oh, incidentally, when you work a neutral compound, the octet number and valence numbers will always come out even numbers. And I'll show you when we get to polyions, which is coming, it won't do that if you just work the elements. So you have to add or subtract an electron because of the charge. We'll show you that in a minute. These are 8 or 2. So this is 1 times 8 plus 1 times 8 again for nitrogen, and then 5 times 2. So 16, 26. Okay. So that's 26 minus 14 over 2, 14, 12 over 2, and 6 covalent bonds. So we come in here 1, 2, 3, 4, 5, 6. The calculation, please emphasize and recheck this in your mind, is bonded pairs. So this is the number of bonded pairs when you do all of this little calculation. It does not represent the non-bonded pairs. You have to put them in intuitively. What does that mean? It means you got to know that when you draw a circle around nitrogen, you got to fill in an electron pair, and that completes the octet. Well, nitrogen group 5, if you have an element out of group 5 in a molecule like this, it's going to carry one non-bonded pair. Okay, so, and those are very reactive type situations, which we'll learn about in dynamics here shortly. Everybody okay on this? Well, this represents single bonded elements, where everything is bonded out one electron pair. And you recall there are single, double, and triple bonds in existence. There are no 4-bond structures like that. There's only single, double, or triple. And the strength of bond, just in passing, because I put this on the quiz next time, you have more electron pairs between elements, you have increasing strength of bond. Is anybody missing last class that did not get one of these little tables? Everybody get one of these little tables? Well, if you look at the bottom down there, you'll see some of these bond energies just in passing, so you can add this to your knowledge base. A single carbon-carbon bond is 346. So if we kilojoules, when a single bond is, this will give you a delta H bonding energy of 346 kilojoules. If you form a double bond, you come down here and you look in this table, and the bond energy, total bond energy, is 602 kilojoules. That's the energy liberated when that bond is formed. Or if you have a triple bond, 835 kilojoules. So that's what I'm trying to tell you, is that there exist single, double, triple bonds, and the more stuff you put between the elements, like a bonding glue, the stronger the bond. Now, depending on, those are all carbons, but if you change it to, say, a carbon nitrogen like that, or a carbon triple bonded to a nitrogen, and that capacity, so changes your energy. I mean, this is double bonded nitrogen, carbon nitrogen is only 615, triple bonded carbon nitrogen is 887. So these don't always match triple bonds. It depends on the fact that it's got multiple bonds and the elements. You have to take that into account. Now, you have to have the table to determine that. So that will be supplied on the test day. So that's not anything you would calculate. So, just in passing. So we have molecules that have more than a single bond structures. Let's do C. H2O, formaldehyde. Its arrangement, quite honestly, is this. Okay, there's your arrangement. There's no options. Hydrogen is never between elements. Hydrogen's always a peripheral element. The carbons and oxygens and any of the others, they might move around, but hydrogen's always on the perimeter. Okay, so what do we need to count? Valence, octet, and bond numbers. And so we have 1 carbon, 2 hydrogens, and an oxygen, 1 carbon, 2 hydrogens, 1 oxygen. So that is 1 times 4 plus 2 times 1 plus 1 times 6, 6, 7, 9, 10, 11, 12. And so now we have 1 times 8 plus 2 times 2 plus 1 times 8, 16, 17, 19, 20. So your number of covalent bonds in this will be 20 minus 12 over 2, 8 over 2, or 4 covalent bonds. And I just told you hydrogen is never a multiple bond. I didn't say that, but I said it's never a central element between two elements, but it also is never a multiple bond. You don't have hydrogen double bonded to anything or triple bonded to anything. It's always a single bond. So when I look at these bonds here, 1 and 2, that's it. But I put number 3 here in between the oxygen and the carbon. Well, I've run out of element pairs. Well, what do? You still got one more bond to put in. You include it into the element pair that's not a hydrogen. Okay, and that's your double bond or your triple bond. That's where you do between the remaining elements in there, like the electron pairs. Now, if you check your octets, carbon's okay, hydrogen's okay, oxygen is not. It still carries 2 non-bonded pairs. Oxygen groups, group 6 elements carry 2 non-bonded pairs, like that. Acetylene is a triple bond structure, C2H2, and we'll have a triple bond between the carbons, obviously, or a multiple bond, if we're going to have one, will be between the carbons. Carbon never carries non-bonded pairs in the neutral form. If it's ions, yeah, you will have that. But in a neutral compound, carbon will bond out everything. So you need to keep that in the back of your mind. That's called 4 bond sites, 4 valence. Nitrogen has 3 bond sites. Okay, you have 5. Just pass on this. That's your valence for nitrogen. To get an octet, how many more electrons do you need? 3 more electrons. That represents 3 bond sites. That is, elements can connect A, whatever they are, connect there. Whatever's left over is pairs, non-bonded pairs. And so that's what we showed in the nitrogen thing we played with earlier. Okay. Valence is 2 carbons, 2 hydrogens, 2 times 4 plus 2 times 1, that's 10. Octet is 2 carbons, 2 hydrogens, that's 2 times 8 plus 2 times 2. 2 makes 16, 17, 18, 19, 20. Yep. Number of covalent bonds is valence minus octet over 2. That's 20 minus 10 over 2. 10 over 2 or 5 covalent bonds. Well, if I put in the first ones between the carbons and the hydrogens, I'm through with that. Okay? You cannot put any more than that between an element and hydrogen. So we have 3 more bonds, and so they would have to go in there, in that multiple bond structure. You don't have anywhere else to put them. That makes sense? This is not going to get any more complicated than that. And I'll show you how to deal with polyions in a second, and it really doesn't get any more complicated. But it's absolutely critically important that you be able to do Lewis dot structures, because the structural layout defines the chemistry of the molecule. Up to this point, the only thing I've done is drawn 2-dimensional molecules. Well, that doesn't mean anything to anything. It's just a picture of the molecule. What the ultimate objective here in chemistry is to learn the chemistry of the molecule. What does formaldehyde do? What does acetylene do? Why is it reactive? What is it expected to do? By looking at these structures. And we haven't given you the factors on that yet, but we will shortly. Okay. Everybody good on so far? Everything's neutral compounds so far. Now we want to draw polyions. These are molecules that we had that polyion quiz way back when. These are molecules that carry a charge, okay? There are only two kinds of net charges that you'll come up with, a positive net or a negative net. You have -2 charges, -3s. Some of the substances have plus charges, cations. So polyions can be cations or anions. Okay. The reason I say this is when you calculate the valence number, you have to either add or subtract an electron to account, or multiple electrons, to account for the charge that is on that polyion. SO3 has a -2 charge. Well, how did it get a -2 charge? Let me do this. SO3, excuse me. SO3, 2 minus. Well, how did it come up with a -2 charge? That simply means it has an excess of 2 electrons. So when you calculate the valence number, you got the elements, then on the end of it you add 2 on your valence, because that's what you account for the charge. What if you had a cation, ammonium ion? Well, what accounts for the net cation? Is deficiency in electrons. So when you do your valence number, you subtract 1. So that accounts for the deficiency and will lead to the electron. So I think it's 1F2. I don't know. Anyway, I'll show you. Okay. Let's do the ammonium. Okay, that's going to be arranged like this. Okay. The valence number is nitrogen plus 4 hydrogens with respect to the elements. But what caused the positive charge? The loss of an electron, technically. So what we want to do is minus 1 electron. That's how we do that. So the valence now is 1 times 5, group 5 for nitrogen, 4 times 1 for hydrogen, minus 1 for the loss of electron that accounts for the cation. So we have 5 and 4 is 9, then we subtract 1, so your valence number is 8. Everybody okay on this? You only have 2 kinds of issues, positives or negatives. If you have a positive, what do? Okay, you subtract the number of positives on the molecule. If it's a negative ion, you add a couple of them. We'll show you that in a minute, or whatever negative charge you have. Octet rule. You don't have to add or subtract anything. You just calculate it as it was calculated in the AVO-Beck for neutral molecules. You don't change anything. It's 1 nitrogen, 4 hydrogens. It's still an octet, 2 or 8. 1 times 8 plus 4 times 2, that's 16. And then your bond number is the same, octet minus valence over 2. 16 minus 8 over 2. 8 over 2 are 4 covalent bonds. So you come in here and 1, 2, 3, 4. So that satisfies everything. And you check your octet. Now, nitrogen in this has had its electron pair, free pair, or non-bonded pair absorbed in a hydrogen. We'll get to that. But it does not have any non-bonded pair. Everything is octet or duet. So if that's true, you don't have to put anything else. And when we did that methylamine, everything checked out, but we had to come in here in the neutral molecule and put the pair in. But in polyions, you can satisfy all of the bonds and not need any non-bonded pairs, or they'll be completely used up. But There's one little exception. I'll show you that. Okay. Typically a polyion is put in big brackets like that, and then the net charge on the outside the bracket kind of as a superscript. Everybody okay? Okay, let's do that SO3 now. So it's got a surplus of 2 electrons. So when you do your valence number, add a couple of electrons. So your valence number is sulfur plus 3 oxygens plus 2 electrons. Right there. Okay. Sulfur, 6, 3 times 6. Yeah, sulfur, if you look at it, it's right under oxygen, so it's in group 6. There we go, number 16. So it would have a 6 valence. And we got 2 extra electrons that accounts for the 2 negative. So 2 electrons, so I'm just going to put 2 there, like that. And so 6 is 18, 26. The octet number, you don't add or subtract anything, you just do it as a 2 or 8 calculation. You have sulfur and 3 oxygens, so that'd be 8 plus 3 times 8, or 32. You don't add or subtract anything. And then the number of bonds in that molecule are octet minus valence over 2, 32 minus 26 over 2, 8 over 2. That's 6, isn't it? Sorry. Or 3 covalent bonds. This can't be right. Let's see, 3, 6, 18, 9, 21, 2, 3. Oh, that's 2, that's right. 3, 6, 18, 24, 5, 26. 7, 8, 9, 31, 2, 3 covalent bonds. Oh, okay. Threw me off. I was thinking double bonds in there. You don't need double bonds in polyions. Sulfur, oxygen, oxygen, and oxygen. Okay. In a polyion, it kind of departs from the need for electron non-bonded pairs, a certain number. In a neutral structure, oxygen can only carry 2 non-bonded pairs. But in ions, it can carry 3 non-bonded pairs. There's your 3 covalent bonds right there. Now, octets, when you fill everything up, sulfur's going to have a non-bonded pair there, and oxygen will have 3 non-bonded pairs. And you intuitively put these in to fill up the octet. It's a no-brainer. If you use up all the bonded pairs, like we did here, 3 bonded pairs, 1, 2, 3, then what do you do with the rest of it to account for the octet? You put non-bonded pairs throughout the entire molecule, whatever's left over. See, we needed a pair to fill up this sulfur, and we needed 3 pairs to do each oxygen. Well, that's legal. Now, this is only a dot structure. Actually, you have those electrons moving around. That's not part of this. But drawing the molecule this way is acceptable in writing out the structure. And then you put a brackets and a -2 to illustrate the structure. NO2. Let's run that one out real quick. Valence is nitrogen plus 2 oxygens plus 1 electron because it's negative. We have 5 plus 2 times 6 plus 1, 18. Octet is nitrogen plus 2 oxygens. This is 8 plus 2 times 8, 24. So the bond number is 3 covalent bonds. So when we draw this out, we see two oxygens, so I'm going to put those on each side of the nitrogen like that. But I got to get 3 covalent bonds in there. Well, I've run out of spots once I fill those 2 up. Well, put another one in. You can have double bonds between nitrogen and oxygen, and you can put it on either side. The side you put it on, fill up your octet with 2 non-bonded pairs. On the side that you didn't put it on, fill up with 3 non-bonded. That's an acceptable structure. Now, actually, you could draw that extra bond on either side. That's called a resonance structure when you can do that. That's a dynamic issue. All right, so that's net minus 1. So here's a polyion with a multiple bond in it, and that you wind up with 2 pairs, 3 pairs. Perfectly acceptable. The only thing is finish out your element with whatever is necessary to reach the octet. And so you put your bonds in with your bonded pairs, then finish with non-bonded pairs. It'll fit, always. To octet rule. Sometimes elements do not necessarily have 8 electrons. Hydrogen bonding out with 2 is an example of departure from octet rule. The octet rule is just a name for a rule. That's all it is. On test day, you will have examples which of the following would depart from the octet rule, would not conform to the octet rule. So if you have, say, NH3, that would have hydrogen in there, would depart from the octet rule, because each one has only a duet in it. Okay? And you will have departures on the other extreme of this. You will have molecules, and you won't understand this, or maybe you do. If you've had geometry before, it will make sense as you explain it through the molecular geometry. But you have molecules like PCl5, SF6, ClF7. Okay? These are radical departures from the octet rule, but they do exist. 1, 2, 3, 4, 5 chlorides. But in reality, that's not what its structure is. Structure is what we call a trigonal bipyramid. And you'll learn this in geometry section. And you still have your bonded pairs in that structure. SF6, we'll learn it when the proper time. It's an octahedron. But it still bonds each of the elements by a bonded pair only. Okay? ClF7, that's a pentagonal bipyramid, and it will have 7 bonded pairs arranged in space in a weird-looking geometry. So we'll cover that in due time. That's a pentagonal bipyramid. Right here, counting all the dots around the chlorine. Chlorine, of course, would be in the middle, and then you put all the fluorides around. And you fill all those up with 3 non-bonded pairs, even if it's neutral. Okay, so those depart from the octet rule. Now, there's one other issue, and that's called a coordinate covalent bond. coordinate covalent bond is a bond formed where the electrons in the bond come from one element and are delivered into another element. Okay? Ammonia has this two-dimensional structure. Boron trihydride has this structure, and it does exist. But boron doesn't have an octet in it. To generate that octet, both electrons are delivered into the boron structure. And you have a coordinate covalent bond right here between the nitrogen. Of course, the rest of it's still there. Because both electrons came from nitrogen. Now you'll see this pop up in organic reactions many, many times. One structure is called a carbonyl structure that looks like this. It is very, very polar. In other words, it has a strong positive charge right there at carbon because of other electronegative factors and stuff I would talk about later. This will attract something like ammonia derivatives. The electron pair will go in there, and it will form a structure that looks like this. Where the electron pair from the nitrogen, ammonia or ammonia derivative, or wherever the electron pair is free electron pair, will be pulled in. Because the electron pair is strongly negative, you got opposites attract. And so you would generate a coordinate covalent bond. Now the outcome of that's not part of what we're talking about. I'm just trying to define the types of bonds here. The molecule that's formed is still has a bond between it, and who cares after it's formed? I'm just defining, well, a coordinate covalent bond is one in which both electrons come from one element, instead of one element supplying one electron, one element supplying another, like that. So, just by definition.